Okay, class, I think this thing's recording. Okay, we're moving on into chapter 10. Right, I made these notes up yesterday. This is the 10th, not the 9th. The notes were made on the 9th. Didn't get around to creating the video till just this morning. Okay, filters, right? Pretty straightforward ideas. You already have a pretty good idea of what a filter is based on your experience with signals and systems, circuit theory for that matter, right? So, filters are characterized or classified as right low pass, high pass, band pass, and band stop. All right, so we'll look at some of these filters today and learn how to design those based on the presentation in this section 10.5. Make sure you read the text on this. It's pretty clear. I'm going to kind of hit the high points, and hopefully this will be of some value to you. I've got some examples that I'm going to work through in detail so you can follow those as well. Right. So if the right, what we're plotting here for the filter, right, is insertion loss versus frequency. That's some oftentimes with filter descriptions, you plot the output over the input versus frequency, right? So this is really the opposite of that, right? So if the insertion loss is low, then that means in this region, right? Then that means all the powers pass through the circuit at low frequencies, right? So high pass, right? The insertion loss is low at high frequencies, right? So all the powers passed at higher frequencies, right? So this is some cutoff frequency at this position here and position here, right? Now this shows a band pass, right? So all the insertion loss is low, and so from F1 here to F2 here, uh, all of the powers pass through the circuit. So insertion loss, you have to think about it a minute, but right here's a band stop filter. So from this frequency, say F1 to this frequency F2, the insertion loss is high, and so none of the energy in this band passes through the circuit. Right? So some people, you can plot it different ways, but in our case, we're going to end up plotting insertion loss versus frequency, right? And that relates to our scattering parameters. So this is a typical representation of a microwave filter. Right? Okay, so these were all ideal, right? This is a doesn't pass. It passes everything rather from 0 hertz up to some F1, and doesn't pass anything, right, from F1 out to infinity. Right. So, and it's a sharp transition from the pass band to the stop band. So real filters don't do that, right? So over here we show right the ideal response function, and then this shows the actual response function, right? So it doesn't transition from the stop band to the pass band in 0 hertz. It takes a finite amount of frequency space, if you will, for that thing to climb up to the pass band, right? So the slope of this, right, characterizes the order of the filter. By order of the filter, we're going to ultimately just say the number. It's going to be related to the number of. These are passive filters, so it's going to be related to the number of circuit elements that make up the filter. Right, the higher the order, the more circuit elements, and then typically the steeper this slope. Right, and also here that you see that in the passband there's some variation of the insertion loss as a function of frequency. And so this variation is referred to as ripple, right? And so we can control the amount of ripple in the passband uh, by choosing the characteristics of the circuit elements judiciously. Okay, in this stuff here, right, there's lots of information on filters now. This is sort of an introduction, lots of different types of filters. A couple right? There's a Butterworth filter, and there's a Chebyshev filter. The Butterworth has no ripple in the passband, right? So the Butterworth filter will be designed so that this thing is doesn't doesn't vary in the passband, and right, the Chebyshev filter, which is what we're going to study, right, has a sharper roll off. So by allowing some variation of the insertion loss in the passband, we can get this slope to be steeper than we can if we require that there be no ripple in the passband. Right? So putting up with the ripple allows the slope to be higher. If you can't stand any ripple in the passband, then you're going to have to put up with the slope being slower, right? Lower, slower change in in insertion loss with respect to frequency. All right, so those are some general ideas, right? So again, you got to read the text on that introduction, and that's important. What do you need filtering for anyway, right? Let's back out, just zoom out for a moment and discuss that, right? Well, obviously, one application is in modulation and demodulation, right? If you have a signal that's coming into your receiver, right? Typically, you multiply that by some intermediate frequency, right, to shift the information to a lower frequency. But in that multiplication, you'll have higher frequency components too, and you may want to eliminate those, right? So you may want to pass the product through a low pass filter. That's just one application of filtering, right? Another application is to eliminate through a band stop filter an interfering signal. Right, a lot of times when you make measurements, 60 hertz, right, radiated from the power lines or multiples of 60 hertz, 120, 3 times 6 is 18, 180 hertz on up, dot, dot, dot on up the spectrum might be causing some interference in your circuitry, and you may want to put a band stop filter, a narrow band stop filter around some frequency that's uh, causing interference. Plenty of applications for filtering, lots of different applications. Those are just two that happen to come to mind off the cuff. I could think of others as well as you. You could think of others too. Sorry, sipping on my drink. All right. So, all right, what are we going to study here? Let's get down to something specific. All right, we're going to learn how to design a Chebyshev filter. Right. So there's if as you read the text here, you'll find out there's basically two circuits that we can start with that's going to give us the desired filtering characteristics, right? So we can start off with this circuit, right? So here's your source, right? And there's some impedance associated with the source, right? This would very often, or pretty much throughout these design examples that Sue does in the text and the ones that I'm going to work through here, this is going to be 50 ohms eventually, right? So the internal impedance of your generator is assumed to be 50 ohms, right? And then the load is assumed to be 50 ohms. And so here's your filter that you're going to be designing, right? And so these G values, right, are going to be looked up from a look. We look up the value of the G values from a table, or the G values rather are specified in a table. So note now this starts off shunt for this particular, and this fundamental design here is low pass. Okay, so uh, the circuit as shown is going to be low pass, but we're going to also discuss how to convert the low pass circuit into a high pass or a band pass or a band stop, right? So the starting place is a low pass circuit, and then we can convert or transfer that into a high pass, band pass, or band stop using the techniques uh, yet to be described, right? So there's two fundamental circuits here, right? There's the one that leads off with a shunt C and then follows with series L, right? And then follows with another shunt C. So shunt C, series L, shunt C, series L, dot, 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 ever how many of these you have, right? So that's the number that you have is going to depend on the order of the filter. Again, higher order filters have faster slopes and, they roll off at a higher dB per octave or dB per decade. Okay, or you can go this way, right? This is going to be you're either fundamentally going to start with this circuit or you're going to fundamentally start with this circuit, right? This one leads off with a series element, then series L, shunt C, series L, shunt C, dot, 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 till finally you get to the load. Again, typically 50 ohms. So, right, Stu organizes this nicely now. Uh, so, right, here's the design step. So, again, right, where are we going to start here? We're going to design the low pass filter. So, even if you want to design a high pass filter, that's fine. You're going to have to still start with the low pass version, and you're going to pick either this circuit or this circuit. So, step one, right? Pick the corner frequency and the number of elements and the ripple. Okay, so what do we mean by that, right? Pick the corner frequency. That's where it starts breaking, the number of elements and the ripple, right? So by corner frequency, what do we mean? That's this frequency right here, back for this actual case. So you're going to pick this frequency, right? You're going to pick the number of elements you're going to use. How many G's am I going to have? Am I going to have, you know, just one element, one shunt capacitor, or one series inductor, or am I going to have a shunt cap, a series L, or a series L and a shunt cap, or how many of these elements am I going to use, right? And then I'm also going to specify the ripple, right? So it's how much ripple I'm going to tolerate. In other words, am I going to tolerate 3 dB ripple, 1 dB ripple, or a 0.1 dB ripple? Okay, so once I specify the ripple and the corner frequency, right, then I'm going to have to put up with whatever I get for the slope, depending on, again, the number of elements. So then, right, after you make that decision, right, you're then going to select the normalized values. What do I mean by selecting normalized values? There's a table in here we're going to look at momentarily. And, right, so when I select the normalized values, that just means I'm going to pick the G1, G2, G3 values. They're going to be given in this table. And then, right, so, uh, and then I'm going to pick G0, right? It's going to be Z0 R naught. So G0 and G sub n plus 1, right? G0 and G sub n plus 1 are frequently going to be 50 ohms for our work. Okay. In fact, in everything that we do here, it's going to be 50 ohms. Does it have to be? No. You can adjust for other values should that be more appropriate for your particular application. So G0 and G sub n plus 1 are going to be our characteristic impedance that we're working with, or, in our case, 50 ohms. Okay, page one. So then once we hit our our G sub n values, right, then we can determine, right, then we can determine our values of inductance and capacitance in our low pass filter circuit. How are we going to get those? Well, as you'll read, right, we define an L prime that's desired L times R naught, and the desired C prime, which is C over R naught, right? And so then L prime prime is L prime over the corner frequency, radian corner frequency. Be careful that's 2 pi times F corner, right? And then C prime prime is C prime over omega sub C. So then we could just make these substitutions. And so it's going to be the inductance value that we're going to use in the circuit is going to be R naught, again, very typically 50 ohms, or in every case, 50 ohms, times the G value from the table. We're going to look at that momentarily, divided by the corner frequency. Okay, this is low pass, right? We're doing the low pass design first, and the corresponding capacitance value is going to be the G value from the table divided by R naught, 50 ohms, times the radian corner frequency, 2 pi times the uh, corner frequency in hertz. Okay, so right, so obviously the next step would be to look at the take a look at an example, a simple example. We're just going to follow the one that Stu does. So now let's look at that table real quick, though. That's important because that's where all the G values are coming from. So you're reading through that material, and we're covering it in the notes as well as in the little presentation here. Okay, so let's get that right. Here we go. Here's your table. It's on page 583. So again, let's look at how this thing is organized, right? You've got 1, 2, 3 different tables, 3 different groups of numbers, right? And so each table picks the ripple, right? The table is which group that you use depends on what the ripple is, right? So 0.1 dB ripple means that I just don't allow very much change in the pass band, right? Or stop band or low pass or high pass, right? But here let's think in terms of low pass, and we're going to observe how to change that into high pass. So we just don't allow much ripple in the pass band. Here we're going to allow a little more ripple with these numbers, and then finally we're going to allow more ripple still with these numbers. Right? And so first pick the ripple, that puts you in one of these 3 tables, then pick the order, right? Then pick the order, right? And so it's going to give you, so if I want 0.1 dB ripple and I want a third order filter, then my G1 value is going to be 1.0315, right? My G2 value is 1.1474. My G3 value is 1.0315, and then G4 is going to be 1, which is the output resistance value. And so when we convert that, that's going to be 50 ohms, right? So these 3 values in here, right, depending on whether I pick this circuit, right, whether I pick this circuit or this circuit to start with, are going to describe my inductance and or capacitance values, right? So these G values are going to be converted, just as we discussed, into inductance or capacitance values, depending on whether I pick, right, 1031A to start with or 1031B to start with. Okay, it may seem more complicated than it actually is. So let's do an example. That usually makes things much simpler. Right. Show me what you're talking about. Okay, so let's work the simplest possible example, right? First order, right? N equal 1, right? The order is the number of elements. We're going to design a low pass, and we want 3 dB ripple. Okay, and we're going to, and our corner frequency is going to be 1 gig, right? So we're thinking microwave frequencies. Right? And we're going to be operating with a 50 ohm system. Okay, so now everything is specified, right? The filter characteristics have been specified with this statement. Okay, and so then you got to decide whether you're going to start with, right? Am I going to use 1031A or am I going to use the dual circuit 1031B? You've learned about duality. Duality is in lecture as well, for that matter. Okay, so very good. So in this case, we're going to pick the A circuit. And so, right, then we're going to have, right, it's first order. So since we picked the A circuit, we're going to start off with the source, 50 ohm internal impedance, a cap, right? None of these elements will be in here. And then we're going to terminate with another 50 ohms, right? So the topology looks like this, right? Source, G0 is 1, G1 is a cap, and G sub n plus 1 is going to be 1, 2 from the table, right? So, right, from table 10.3, right, we're back over here now. So we're 3 dB ripple, right? We're 3 dB ripple, so we're down in this table, right? And it's first order, and so the number is 1.9953 for G1 and 1 for G2. So this guy's number is G1 is 1.9953, G2 is 1. And so source 50 ohms, because G2 is 1, that's 50 ohms, right? So here's our cap value. How do we get the actual value of the capacitance, right? It's going to be the number from the table divided by R naught, which we've chosen to be 50 ohms, times omega C. So it's the value from the table, 1.9953, divided by 50 times the break frequency, right, which is 1 times 10 to the 9, 1 gig times 2 pi, because it's omega C. So I've just used this formula right here. So there it is, right? So simple low pass, low pass circuit, right? Source 50 ohms. Here's my uh, single element, and then here's my load, right? Right. So this is low pass, right? At high frequencies, right? You can imagine some current coming out of here at high frequencies, right? The cap is going to be a short circuit, right? 1 over j omega c. So all of the current will go this way, and none of it will go to the output, right? So at high frequencies, the insertion loss is going to be large. At some corner frequency and below, right, this impedance is large, so most of the current's going to go through the 50 ohms, and so then the insertion loss will be small. So it would then be, right, again, if you're going to plot insertion loss versus frequency, you're going to see something like that. Right? It's going to be sloppy because there's only one element. So this is low pass. So the table is designed to give you low pass right out of the blocks. Right? That's the way. Learn how to convert that here in a little bit. Okay, straightforward. Right, straightforward. Uh, okay, so all of that, right? And Stu has some other examples in there too. I've just picked the first one, so you're going to have to follow the other examples in the text, and they're pretty straightforward now. I think you can follow that without much effort. Read the text, look at these notes, work the homework, and I think you'll be in good shape on this stuff. Okay, so now how do we do a high pass design, right? How do we do a band pass design? How do we do a band stop design? And so the answer to that, as I mentioned earlier, we're just going to modify the low pass design in accordance with table 10.4. Right, so this table 10.4 is crucial. So let's go and take a quick look at that, see how this thing works. Okay. 10.4 is uh, the table 10.4 is critical to how we do that, right? And so, right, if you have you'll have a low pass design, right? And so you'll have inductances and capacitances in your low pass design, right? And so uh, every low pass filter, the inductance value is L prime divided by omega C, right? Well, that's your corner frequency. and every capacitance in the low pass design is C prime divided by omega C. Now, if you want to make that high pass, right, here's how you do it. Wherever you see an inductor in your low pass circuit, you replace it with a capacitor. And wherever you see a capacitor in your low pass circuit, you replace it with an inductor. That kind of makes sense, right? Because the frequency dependence of an inductor and a capacitor are reciprocal to one another, right? So if you want to make low pass into high pass, you need to replace inductors with capacitors and capacitors with inductors. Now, on the other hand, right, if you want to build a bandpass filter, right, you're going to replace the inductor with a series inductance capacitor, and you're going to replace the capacitor with a shunt inductance capacitance combination. Okay, and if you want to make a band stop filter, wherever you see an inductor in your low pass circuit, you replace that with a shunt uh, inductance capacitance combination, and you replace every capacitor in your low pass design with a series inductance capacitance combination to design a band stop filter. Okay. Now the values of these, right, are going to depend on things like, right, particularly when we're talking about bandpass filters, we're talking about a range of frequencies, right? So you've got an upper and a lower here, and so the bandwidth, the radian bandwidth is going to be the upper radian frequency divided by the lower radian frequency, where omega naught, right, is the geometric mean between the upper and lower frequency. Okay. Bandwidth is radian upper frequency divided by omega lower frequency, and omega naught is the geometric mean or the square root of the product of the radian upper frequency and radian lower frequency. Okay, so right, that's pretty straightforward, right? This table tells you how to design low pass, high pass, band pass, and band stop. And again, right, with all of these, right, you still have to decide, right, there's two ways to do it, right? There's two circuits that you can start off with. One is going to be the 1031A circuit. I can always start from here, or alternatively, I can start from here. Which of those is best suited to your application depends on uh, things and stuff not necessarily discussed at this point, right? You don't know that until you work on the design. All right. Right. So what's the next thing to do? All right, let's work an example. So we're going to move away from the simple low pass, right? And we're going to move to a high pass. Okay, so, right. Uh, so if I'm going to go high pass, how am I going to do that, right? First of all, I'm going to pick uh, either A and B to start with, right? In this particular case, we're going to pick B, right? So I'm going to lead off with an inductor, followed by a shunt capacitor, and then the third element is going to be another series inductor. So it's going to go LCL. So it's LCL, right? Uh, and so then we stop because it's three elements, third order, right? We're specified to be third order, right? Again, we're going to do 50 ohms, Z naught 50 ohms. I don't know if that was stated or not, right? And so, right, I know immediately that this is 50 ohms and the load is 50 ohms. So I'm trying to make a high pass circuit, right? So this is the low pass topology. It leads with an L, follows with a shunt C, and then another L, right? So when I convert this over from low pass to high pass, right, how am I going to do that? Well, everywhere again, right, that I see an inductor, I'm going to replace it with a capacitor, and everywhere I see a capacitor, I'm going to replace it with an inductor, right? So it's turned into a C. C gets turned into an L, and the L gets turned, right? Third order, third point one, go to the table, 0.1 dB ripple. That puts me in the A table. Order so G1 or 1.315, 0.1474, and 1.0315 again. So these two values, circuit elements for the same, but the value of the element will be different. Again, this is going to value, C value, L value. Well, I said that wrong. The C value, L value, C, L, C. Well, how do you get it, right? Go to the table. Again, that table is critical. It's going to be the C for the high pass 1 over omega C L prime, right? But L prime is the number times R naught. So it's going to be 1 over omega C, the number. So it's, right, 1 over omega corner, which is 2 pi F corner. We're doing this thing 2 times 10. Right? The number from the table is 1.0315 times 50. Right? So that's got to be 1.543 picofarads, right? 10 to the minus 12. When I do the L value, right, what's my L value going to be for the high pass filter? It's going to be 1 over omega C times C prime, but C prime is G sub I R over R naught, or G sub I over 50. And so the G sub I is going to go in the denominator, and that flips it over, right? So the R naught is going to go in the numerator, or it's going to be, for the inductance value, 50 divided by 2 pi times 10 to the ninth times 50 divided by quantity, 2 pi times 10 to the ninth times the second value from the table, which is 1.1474, and that gives us 3.468 nanohenries, right? And then this C is the same because the value of the table, the third value of the table is the same as the first value from the table. So voila, right, we've got our design. Source, 50 ohms, 1.543 picofarad for this cap and that cap, and the shunt inductor in between is 3.468 nanohenries, and then that's 50 ohms. So you can see figure 1036 for the response plot, right? Let's look at that. Figure 1036. Right, it's going to look like this, right? 1036. So this is high pass, right? So the insertion loss at high frequencies is low, right? But the insertion loss at low frequencies is high. So it's obviously not, it's obviously not the ideal case. And so because of the order of the filter, this thing has got slope. Okay, and then you note too, right? We designed this thing for 0.1 dB ripple, right? So you don't see much change over here. You don't see much change as a function of frequency. So the ripple is confined to be very small, 1/10 of a dB, which is essentially no ripple for that matter. Okay, right? Interesting how this stuff works. All right, continuing. Right, trying to move our way through this. So let's do something a little more challenging. Right? Let's work some of the problems in the back, and this one we're going to go through all the way from start to finish. Right. So here we're going to start with 1031B. Right. Again, right. Pay attention now. We got you're always going to go either. Remember how this works. You've got to decide is this your fundamental low pass circuit topology, or am I going to use the dual? Pick one. Okay. Pick one. And so in this case, we're going to go with 1031B. And so it's going to be LCL, Series L, Shunt C, Series L, Shunt C, Series L. Okay. So we want third order, right? And we're going to go for band pass this time. We're going to go for band pass. We want a 50 ohm system. And so our pass band is from 900 megahertz to 1100 megahertz. Okay. Or 0.9 gig to 1.1 gig. Okay. And we're going to allow for 1 dB ripple, right? That sends us to the right table. And then when we're all through designing this thing, right, the intent is to actually draw the circuit with the appropriate inductance and capacitance values, and then go through the circuit analysis to plot the insertion loss versus frequency using something, MATLAB, uh, some sort of circuit analysis code, MATCAD. You pick one. I don't care. I used MATLAB just because I'm used to it. Maybe you could even do it with your calculator. I don't know. Give it a whirl. Okay, right. So, right, the low pass design is LCL, right? LCL, and let's go quickly remind ourselves how this works. First, I designed the low pass design, right? And I'm wanting 1 dB third order, 1 dB ripple third order. So that puts me in the middle table, third order. So my numbers are 2.0236, 0.9941, 2.0236, and then 1 again, which is going to manifest itself as a 50 ohm. Right. So I just sketched that this way and just put those raw numbers next to these the inductance and capacitance. So remember, so this thing, pay attention to this is low pass. That's the fundamental. Now, right, so our low pass is going to be source 50 ohms, L, C, L 50 ohms, right? So we're going to convert that into using the table band pass. How do we do that? And remind ourselves. So, right, to go to band pass, every time I see an L, I need to replace it with a series LC combination. Every time I see a C, right, in the low pass design, I need to replace it with a shunt LC uh, element, right? So inductors gets replaced with series inductance capacitance. Capacitance get replaced with shunt inductance capacitance of these values, right? It tells you how to get the values. These values depend on L prime and C prime, right? And L prime and C prime depend on the table values, right? And the corner frequency and the impedance that you're using, right? And again, in our case, R naught's always 50 ohms, right? Right. So, right, our L got converted into a series LC because I'm going for bandpass. My C got converted into a shunt LC, and then the L this next series L is another series LC. Right, right. Since the numbers since G1 and G3 are identical, these elements are identical. This element's different. Okay, so again, according to the table, L1 is G1 times R naught over omega naught minus omega L. Where did that come from? Right here, right there. L prime over bandwidths of omega, the bandwidth in the radian bandwidth, omega upper minus omega lower, right? Omega upper minus omega lower and then L prime is right G1 times Z naught, so it's G1 times R naught, right? So you can see down here, I'm actually calculating that. The G1 value is 2.0236 times 50. When I divide, so that's going to be 2 pi times 1100 minus 900 hertz. And it's megahertz, so it's times 10 to the 6th. So L1 is going to be 80.5 nanohenries, right? L2, right, according to the formula from the table, it's going to end up being 1.617 nanohenries. C1, right, is going to be, according to the values in the table, 0.3177 picofarads. You can look at my chicken scratch down here and see how I computed these numbers now. And then C2 is the value from the table divided by 50 times 2 pi times the radian bandwidth. Turns out to be 15.82 picofarads. Okay, so now, right, I got all my circuit values. So now I can draw the bandpass design, right? Source, 50 ohms. Here's my element, first series element, right? Here's my first shunt element, and then here's my next series element, which is identical to the first. Okay. So, right now we've got the design. Let's check it, right? We want to actually be able to use our numerical tools or whatever technique to do it by hand. My gosh, that would be a pain. But use whatever numerical tools might be handy for you. P-Spice, right? That's another good way of doing it. Create the circuit pretty quickly and get the frequency response from it. I'd use MATLAB again, and I'll show you how I did it, but I don't necessarily intend to try to argue that that's the best way. The best way usually is the way that the engineer is most familiar with. Right? Okay. Everybody's got their favorite hammer, right? Okay. If no filter is in place, right, we're trying to get the insertion loss, right? So we need to know what the output is when the filter is not there, and then we need to get the output when the filter is in there, right? And that will give us the ability to determine the insertion loss. In other words, I'm taking my circuit, I'm inserting it between the source and the load, and the question becomes how much loss is there due to this insertion of this thing, right? Well, since it's a band pass filter, there should be a range of frequencies over which uh, it doesn't, uh, the insertion loss is low, right? Outside of that band of frequencies, the insertion loss should be high. And based on the design, right, the order of the design is the slope of the skirt slope going from band pass to band stop, and also the amount of ripple that we're allowing in the pass band, right? In this case, 1 dB. All right, so all of that, right? So this is right. If no filter is in place, right? The output is just going to be V, right, times 50 over 50, 50 over 50 plus 50, or right, V over 2. That's if no filter is in place. Now, when the filter is in place, I need to figure out what the output is. Well, right, how are we going to do that? Well, you got to use circuit theory, right? So in this case, I just did it via mesh analysis. Could you do it via nodal analysis? Sure, you could. Maybe it's more convenient to do it that way. I don't know. I just picked one and pursued it. Okay, so right, it's write a loop. I'm going to write a loop. Kirchhoff's voltage law in the first loop. Kirchhoff's voltage law in the second loop. Then I organize this in a matrix form. Right. Some of you have been trained to go directly from here to here. That's fine. Just make sure you get it right. 5, page 6, right? So I need to solve for I2, right? And once I get I2, I can multiply it by 50, and that will give me the output voltage. once I get I2, once I can multiply it by 50 and get the output voltage. And that'll be obviously a function of frequency, right? So I2 is a ratio of determinants, right? And so I do the arithmetic. This one times this one minus this one times this one gives you Z2 times V. And then this one times this one minus this one times that one, right? That's your denominator. So V out is 50 times I2, so then you get a 50 here. So here's my output with the circuit in place, right? With my bandpass filter in place. And then on the previous page, right, I've got my output with the circuit removed. Okay, so those are the two quantities that I need, right? So my insertion loss is defined as 10 log base 10 of the power available, right, divided by uh, the power with essentially the circuit in place. Okay. So the power available is V squared over 4 times 50, right? I know my output, uh, this is the power available from the generator, right, is V squared over 4 times 50. How does that come about? Real quick, there's V, this is 50 ohms, right? The available power uh, is when the load the generator sees is matched to the generator, right? And so this is going to be V, and so the current is I divided by I squared times R. So the current is V divided by 2Z naught squared times Z naught. And so that's V squared over 4Z naught squared times Z naught. Or you get a Z naught canceling, and so it's V squared over 4 times 50. Okay, so that's available power. Hopefully I didn't stun anybody with that one. It's the available power from the generator. You compute that by allowing the generator to drive the conjugate of the generator's internal impedance. In this case, since the internal impedance of the generator is 50 ohms, you allow the generator to drive 50 ohms and then compute the power absorbed by that. That's this number. That's power available. And the power delivered to the load is V out squared divided by 50, right? The magnitude of the output voltage squared divided by 50. Okay, so now we got everything we need, right? Because V out, right, it's in terms of V, and P sub A is in terms of V, power available, and so that's going to cancel out of the circuit. So, right, and I'm insertion loss is 10 log of that, 10 log base 10 of that, and so there we go. And so I'm plugging in from the previous equations, right? So there's some manipulation here. You can follow that, and it's pretty straightforward. Now, note the V squareds cancel out of this, and then I've got a fourth times this thing. I got a fourth times this thing. And so I've got log of A times B is the log of A plus the log of B. So I'm going to just take and add 10 log base 10 of a fourth to this part of it, which is the frequency dependent part. Well, that manifests itself as a minus 6 dB. So it's going to be, this is squared, 10 log base 10 of something squared is 20 log base 10 of the thing. So it's 20 log base 10 of this ratio minus 6 dB. All right, so now I'm ready, right? I'm ready almost to go to the computer. So I got to get Z1. It's J omega L1 divided by plus 1 over J omega C1. Z2 is 1 over Y2, right, which is 1 over J omega L2 plus J omega C2. And then here's all my L and C values that I computed from my circuit. Right, 6. So with that, right, everything's defined, right? So the impedance values are a function of omega, obviously, right? So they're a function of frequency. So this thing is going to be plotted or we'll plot the response, the insertion loss versus frequency. And so that's what this code does, right? MATLAB, right? So real quick here, I'll run this, zoom in, right? So I create a range of frequencies. I convert that into radians, radian frequency. Here are my inductance and capacitance values. Here I'm computing the impedance, Z1. I'm computing the admittance Y2, and Z2 is a reciprocal of that. And so then my response is, right, according to the formula from the previous page. And so I'm going to plot frequency versus 20 log of, right, the absolute value of the response, because it's magnitude, remember, magnitude minus the 6 dB. And then I just told it to hold on, and then I'm going to plot the 3 dB line, right, so I can see where the 3 dB line intersects my response function. Okay, so you can study that. You know, you're a MATLAB guru, or you might not like this, right? So go use PSpice or whatever else you like. Program it on your calculator. Use MathCAD. Use a supercomputer. I don't care. Just get the answer. Okay, so I fiddled around. Of course, whenever you do this, you make a few mistakes. So it took me a minute or two to knock out the errors in my MATLAB code. Typos. What was it? Typos. I had log rather than log 10, so it was taking the natural logarithm of it. So the curve looked right, but it had the wrong values. Had to fix that. I forget what else. But anyway, a little troubleshooting, maybe 10 minutes of troubleshooting, and away it went. The frequency range, I had to play around with that to get something acceptable. I went too wide or something. I forget what it is. So voila, right here's our response function out of MATLAB: insertion loss versus frequency. And so this thing, it's band pass, right? So the insertion loss is low over the range of frequencies. And then as you move away from that range of frequencies, what was it? It was 900 and 1100. And there's your ripple, 1 dB ripple. So here's your 3 dB line. That's about right, right? 1, 2, 3. So the ripple is not more than 1 dB. Okay, so it worked out. Okay, it worked out pretty good. It's a way to do it. Is it the only way to do it? No. Do you have to do it that way? No. But you've got to get the right answer. Right? So you do it your way. Just make darn sure you get the right answer. I've given you this. You can follow this kind of code, or maybe PSpice is a better way to approach it. Right. So here's some homework. Run that same problem that I just did, but make it band stop. Right. My 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 formula or my design was band pass. You turn around and make it band stop. Same characteristics. So draw your circuit and then plot your response, and then I'll work through that and put that out on the engineering FTP site pretty soon. Okay, that's the note for today. That's the little video for today. The notes will be either already out there or will be. The video will be uh, posted uh, momentarily. Okay, hang in there, keep going. Got one more section to do, I think. One or two more sections. Amplifier.